Good morning everyone. So recall that in the last class we have discussed how do we write down the generating function for the problem of selection with repetition without repetition, and then from the generating function how do we find the coefficient of x raised to the power r. Now in today's class we will introduce a new concept which is partition. So partition of r identical objects divide the group into a collection of subsets of various sizes. Better to understand, partition of integer r is a collection of positive integers whose sum is r. Yes, so positive integer is very important. So for better understanding, let us try to compute all possible partition of 5. Please do try it by yourself. So after trying it, you will realize that there are 7 possible partitions as follows. But now if we have to write down the generating function for computing the number of the partition of integer 5, then how does it looks like? Yes, so if you recall that in general we used to write down er where r or en where each ei starts from, if there is no restriction, from 0 1 2 and so on. Yes, now let us consider 5. If I write it as 1 plus 2 dot 2, if I consider it as e1, so the value of e1 is, I have taken 1, and if this is e2, so I have taken it as, its value is also 1, where e2 is 2. But the problem here is that it is coming 2 times. Yes, so it is coming 2 times, so e2 is, sorry, 2, because it is coming 2 times, but at the same time its contribution is not 2 but it is 4. So this is very important. Now you see it as like this. For example, you pick 3 pairs of the socks. If someone asks you how many socks you have taken, then you have said 3 pairs, which means 6 socks, but exactly you have taken the 3 pairs, so ei is 3 but it is contributing 6. If there is a bundle having 3 books and you put 10 bundles, then actually you have picked 30 books. So if ei is 10 but its contribution is 30, it means that instead of this equation, it's better to write down that e1 plus 2e2 plus 3e3 plus er is equal to r. Yes, so if I say e4, it means I am picking a bundle. If e4 is 4, I am picking a bundle, only one bundle, but in bundle there are 4 items are there, so its contribution is 4 multiplied by 1. If I am picking 2 bundles, its contribution is 4 multiplied by 2. So therefore this is how it looks like. Yes, and then I can write down each, where each ei is, as we used to write down, 0 1 2 and so on. I can also write down in the another form, x1 plus x2 plus xr is equal to r, or you can write e1 plus e2 plus e3 plus er, where x1 is simply 0 1 2 so on, x2 is 0 2 4 and so on, x3 is 0 3 6 and so on. So now it means if I have to write down the generating function, then my generating function would be, from here it is g of x, so x1 is 0 1 2, so 1 plus x square and so on, x2 is 0 2 4, so 1 plus x square and so on, x3 is 1 plus x cube and so on, and goes on and goes on. So this is how we can write the generating function in the case of partition problem. This is how it looks like, and I can further simplify it. So I can write it as 1 by 1 minus x, 1 by 1 minus x square, and 1 by 1 minus x raised to the power 4. So this is the required generating function which can be written into this form. Now let's see some questions. So find a generating function AR for the number of the ways we choose 2 cent, 3 cent and 5 cent stamps adding to a net value of R cent. So if you write down the equivalent number of integer solution equation, then it looks like 2e2 plus 3e3 plus 5e5 is equal to R, where each ei is greater than or equal to 0. So the generating function would be 1 plus x square plus x raised to the power 4 so on, 1 plus x cube and so on, and 1 plus x raised to the power so on. Or you can write it as 1 by 1 minus x square, 1 minus x cube, 1 minus x raised to the power 5. Let's move to the next interesting question, which says that show that the number of partition of n into odd parts. So odd part means that you partition 5 as 1 plus 1 plus 3 odd parts, even term are not included, is equal to the number of the partition into distinct part, and distinct part means you write 5 as 2 plus 3. So both are equivalent. It means that we have to show that in both the cases the generating function is same. So if I write down the generating function, please do try to write down generating function by yourself. For the number of partition of n into odd parts, so only odd values are allowed. So 1 plus x and so on, this is the first bracket. The other one is 1 plus x cube and so on, 1 plus x raised to the power 5 and so on, and goes on. So it means that this would be my required equation. Yes, which would look like 1 by 1 minus x, 1 minus x cube, 1 minus x raised to the power 5 and so on. If I have to write down g2x into distinct part, it means that each ei is either it is present or not present. So it is only present once, which means 1 plus x. If I consider e2, it is again the values are 0, 1, so 1 plus x square, 1 plus x cube and so on. Now I have to show that g1 is equal to g2. If I consider g1, which is 1 by 1 minus x, and if I multiply by 1 minus x square, 1 minus x square, then 1 minus x cube, 1 minus x raised to the power 4, 1 minus x raised to the power 4, 1 minus x5, 1 minus x raised to the power 6 and so on, it gets simplified as 1 plus x, 1 minus x, 1 minus x square, 1 by 1 minus x cube, 1 minus x square, 1 plus x square, 1 minus x raised to the power 4 and so on. Now what you observe here is that all the terms in the denominator are cancelling out. They would be cancelled out with the terms in the numerator, and the numerator would have only 1 plus x, 1 plus x square and so on, which is equal to g2x. Since there are infinitely many terms, therefore the denominator terms would be cancelling out, and the numerator we have only the terms 1 plus x, 1 plus x square and so on. That's why g1x is equal to g2x. How many ways are there to express n as sum of integers not no greater than k? Yes, so till now when I am writing 5 also, I am considering 5 plus 0, or I am considering 4 plus 1. But if I put a restriction that no greater than 3, so I can only consider 2 plus 3. Yes, so it means that your equation is e1 plus 2 e2 and k ek is equal to r. and that's why the generating function would be 1 minus x, 1 minus x square, and so on, and 1 minus x raised to the power k. How many ways are there to express n as a sum of integer no greater than k till first part, one of which is k itself. So in the sum k must be included. So if k must be included, which means that your ek, instead of starting from 0, it is start from 1. That's why that bracket would be x raised to the power k plus x raised to the power 2k and so on, and you can take x raised to the power k common, and the remaining bracket becomes 1 by 1 minus x raised to the power k. In total, the generating function would look like 1 minus x, 1 minus x square, and 1 minus x raised to the power k, and in the numerator you have x raised to the power k. So here we are not computing how many ways at this stage, we are only computing the generating function. That's why I simply wrote down the generating function in these two cases. Find the generating function for the number of ways to express r as a sum of distinct power of 2. So when we say distinct power of 2, it means the possible values are 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and so on. And either it is included or it is not included. So you can say that g of x is 1 plus x, because the value of e1 is either 0 and 1, then, or you can say x1, the value of x2 is either 0, 2 raised to the power 1, x3 is 0 and 4, x4 is 0 and 8, and so on. And that's why the bracket is 1 plus x square, 1 plus x raised to the power 4, and so on, which is the required generating function. So till now we have seen that how do we write down the generating function for the problem related to the partition. Now here if you see this image, then it is a partition of all possible partition of 8, such that if the largest number is k, which is 3 in all of them, then it is equivalent to the number of the terms used, which means that we can say that from this image that the number of ways to partition n into non-zero parts, of which largest is k, so largest is 3, is equal to number of ways of partition n into k non-zero parts. So the number of partition of 8 into 3 non-zero parts, which is 5, is same as the number of partition of 8 into the parts where 3 is the largest. So very interesting observation. But the question comes, how do we prove it? If you try by generating function, it's quite difficult. So for this we'll introduce the concept of Ferre's diagram, which says that if I have to write 3, 2, 2, 1, I should put 3 dots, then 2, then 2, and then 1. So this is how the Ferre's diagram is defined. So it is partition where a1 is greater than equal to a2 is greater than equal to a3, and so on, and it is k left justified rows are there. So here you can see that 4 rows are there and 3 columns. So 3 comes from here, so largest is 3, and 4 rows means the 4 terms are used. Now if I have to prove the above result using Ferre's diagram, what I can do is that I can consider its transpose. So if I consider its transpose, then this row becomes column, then this becomes column, and then this becomes column. It means that here the largest is 3, and here the partition would be 4 plus 3 plus 1, 3 terms are used. So there is one to one correspondence between partition of n where largest is k and partition of n into k non-zero parts. It would be clear if we see here. So this is the partition of 15, and if we define transpose, which is known as the conjugate of the given diagram where we interchange the rows and the columns, then this is the transpose. And you can see that here it is the partition where largest is k, 3 to 5 and 7, and then it get transformed into a partition with 7 terms, 5 4 2 1 1 1 1. So here we haven't shown through generating function by computing the generating function showing that the coefficient of x raised to the power r is equal in both the cases. Instead, what we show that each solution where k is the largest has one to one correspondence between a solution where it has been partitioned into 7 items. Yes. So this is the detail which you can read by yourself. There is one to one correspondence between these two classes of partitions. A partition is self conjugate if it is equal to its conjugate. Please think of an example by yourself. So one of the example is 4 3 3 1. If you take its conjugate, it comes out to be same. Now the question comes, prove that the number of partitions of n into parts both are odd and distinct is equal to number of self conjugate partitions of n. Yes. So for example, let's say 9 is there. So one of the partition of 9 is 9 plus 0, which is odd and distinct, which is 9 itself. Or I can see 5 plus 3 plus 1, which is again odd and distinct. Yes. But at the same time I have to show that this partition, or I must be able to find its Ferrer diagram which is self conjugate. So what I can do is that, for example, if I consider 9, so it's an odd number, so I can make a column with 4 and make a row with 4, and the last one I put it here. This is a self conjugate because when you transform a row and column, then row becomes column, columns becomes row. Or if I consider 5 plus 3 plus 1, so I break it as 2 plus 1 and then 2. 3 can be broken as 1 1 and 1, and 1 can be broken. Again it is self conjugate. It means there is a one to one correspondence. If you write down a partition which is both odd and distinct, you can draw its Ferrer's diagram which is self conjugate. So this is what we are saying. Use this Ferrer diagram. A bijective proof is straightforward. The general idea is to band each odd distinct part at the middle cell and join the band pieces together. This yields a self conjugate partition and a process that is clearly reversible. So that's all from today's class. In next class we will see how to write down the generating function in the case of arrangements. Thank you.